The last topic of this lecture is relative motion analysis. Relative motion analysis and differentiation of geometric constraints. Now, this is a long title, but it's a very simple topic. So let's start with something very simple, and I'm going to give you an example. Let's say you are driving a car, okay, and we'll call this car A at a certain speed, and this speed is, let's say, 55 miles per hour, okay. And on the same road behind you is your friend driving a car. Let's call that car B, driving at a speed of, let's say, 30 miles per hour, okay. So if I ask you, what is the speed of A as seen by your friend B? So in other words, what do you think your friend B would perceive your speed as? You would be able to tell me that it actually is going to be a difference between the two. So velocity of A with respect to B, and this is how we'll write it. So velocity of A with respect to B. So notice how A is, above, and then we have a slash, and then we have B. That's how we write velocity of A with respect to B as velocity of A minus velocity of B. And that would be 55 minus 30, and that's 25 miles per hour, right? And that's very simple. If the two velocities were same, then it would seem to be as if A was not moving at all, because the relative velocity between the two would be zero. So that's the basic idea behind, relative motion when things are moving in a straight line, right? Now the question is, can this be extended to motion of particles moving along arbitrary paths in a plane or in space, right? So we want to see that too. The next question is, where does this really come from, right? How do we really know that velocity of A with should B is equal to velocity of A minus velocity of B? And then the second question is, are there any restrictions on when you can apply this formula to compute the relative velocity? So yes, even though you have probably done this for a long time, you probably don't know what are the constraints under which this is really valid. So let's look at some of those things. So for our rectilinear case, what we will do is we will have a reference frame, okay, with an origin, and here is my particle A, and here is my particle B, okay, and I can indicate the position of A with one position vector. We'll call it RA, and we can indicate the position of B with another position vector RB, all right, and we can write that RA is equal to RB plus another position vector, which we'll call R of A with respect to B. And we can write that, that's not a problem. So this is basically just obtained via using the law of addition for vectors. If you differentiate this equation once, what do you get? D over dt of RA equal to d over dt of RB plus d over dt of R of A with respect to B. And what is this quantity? This quantity is velocity of A, this quantity is velocity of B, plus this quantity is velocity of A with respect to B. So it turns out that we have a very simple formula for computing the velocity. Velocity of A with respect to B is going to be equal to velocity of A minus velocity of B, which is what we used before. If you differentiate it once more, you will get the relative acceleration between the two particles, and that would be given by this, right? Now, when we apply this analysis, when we get to these two final formulas, we are essentially assuming at all times that our observers, in this case, the observer is actually A or B, either of them, because both of them could be moving, are actually translating frames. So whenever we talk about relative velocity, relative acceleration, and we use any of these formulas, we are assuming that our observers are actually translating. So what does that mean? Now let's look at this in a more general way when A and B are moving along arbitrary paths in a plane. So we'll start with now a two-dimensional coordinate system, let's say OXY, and we have A moving along a curved path, we have B moving along another curved path. Okay, and we are interested in understanding how A moves with respect to B. So B becomes our observer for A. So we have one reference frame over here, which is basically a fixed reference frame. And then we have another reference frame attached to B, okay? And we'll call it, small o, and then we'll call it x prime and y prime, right? Maybe we can call it O prime. And this reference frame that is attached to B is supposed to be a translating reference frame. So by definition, when something is translating, it is not changing its orientation, or in other words, it's not rotating, which means that, B could be here this instant, next instant B would be here, but the reference frame attached to B would still be pointing this way. Okay, so it's never changing its orientation because it's not allowed to rotate while A is moving along this path. So velocity of A could be, let's say, VA, and velocity of B, which would be tangent to this path, would be VB. So now the question is, what is the velocity of A with respect to B? So let's start by showing the position vector. So this is R sub A, this is R sub B, and notice how I'm drawing these position vectors with respect to the origin of my fixed reference frame. And we have the position vector of R of A with respect to B. Okay, so this is all shown in fixed reference frame. So we can write R of A is equal to R of B plus R of A with respect to B. And if we differentiate it, we will have d over dt of RA equal to d over dt of RB plus d over dt of R of A with respect to B. So these two things are, fairly understandable to us. This is velocity of A, this is velocity of B. What is this quantity? And we've seen that this quantity is supposed to be velocity of A with respect to B. But the question is this velocity measured in the fixed reference frame, the fixed reference frame being OXY, or is this velocity measured in O prime, X prime, Y prime, which is the moving reference frame? So this is fixed frame, and this one is moving frame. So let's think about that for a minute. It turns out that this velocity, the relative velocity of A with respect to B, whether you measure it in the fixed reference frame or this translating moving reference frame, it's not going to be different from each other. The reason is d over dt of R of A with respect to B basically measures the change in this position vector over time, right? And what is that change? That change is basically this vector R of A with respect to B itself. A vector is defined by its direction and magnitude. Direction is not changing in this case. The magnitude is not changing either in the two reference frame because this is really a difference between the two position vector. Now, a particular position vector could be different between two reference frame, but the difference as shown over here is not going to be any different between the two because B is moving with a translating frame. Now, if B was not moving with a translating reference frame, then that would be a problem. Why? So let's look over here. So this is the reference frame O prime, X prime, Y prime. This is your moving reference frame. In this moving reference frame, we have this vector R of A with respect to B, which I'm going to show now in a different color. R of A with respect to B. And let's say at a particular instant, it's making an angle theta. All right. After a while, this could be over here. Okay, and it's not rotating. This frame is not rotating. So whatever this direction was could be maintained, or it could be another, let's say theta prime. All right. So because this reference frame is translating, the magnitude of this vector as well as the direction is same in both fixed as well as moving reference frame. If you allow this vector to rotate, if you allow this frame to rotate, all bets are off because now it is making one angle. This vector is making one angle with respect to fixed reference frame, but making another angle with respect to rotating reference frame. So we can write this as velocity of A with respect to B with the understanding that this could be measured either in fixed reference frame or moving reference frame as long as this is a translating frame. And that's the key point. That's the constraint. So for the translating frame, this relationship would be valid. You can differentiate it once more and you would get this as your new relationship that would relate the acceleration of the two particles.